we discussed in the last lecture was on deadlock avoidance. We discussed about deadlock prevention technique also. In prevention, we try that the four conditions should not hold at same time. So we worked on it, and we found that the only condition of circular weight, we can actually get rid of that. For getting rid of circular condition, we used numbering for the resources. So the numbering of the resources would be based on some sequence. We allocate the integers to the resources, and we enforce that if a thread wants to use a particular information or resource, then it should be greater than the previous one. That is how it is basically used. So now then we start a discussion about deadlock avoidance, and we discussed about the safe state, and which is basically saying that if the system is in a safe state, then there are no deadlocks. If it is an unsafe state, then there is a possibility of the deadlock. So avoidance is to ensure that the system will never enter unsafe state. So for that, we have a safety algorithm. Now, there are two methods that can be used for avoidance. One is a resource allocation graph, which is modified by adding a claim edge, and we have multi-instance of resource type using Banker algorithm. So we discussed about these two approaches, and we also discussed about how we can calculate. Here is a resource allocation graph. We added a claim edge. Claim edge is basically used for representing the future request. So if there would be a future request for a particular resource, based on this condition, to judge the cycle or detecting the cycle in a graph is super easy. So once the cycle is detected, we can say that there would be a deadlock condition. Now this is single instance. So if you remember, the sufficient and necessary condition for a deadlock is when resources have a single instance and there is a cycle in the graph, then we can say that deadlock would surely happen. In other case, if we have more than multiple instances available with the resources, then we may say that it may or may not happen. If you remember, if let us suppose all our resource R1 has 3 instances and each one is in cycle. So each one is in some cycle. So then we can say that we have to judge which cycle it is, what dependency it is there. So this could lead to a deadlock condition. But if one resource is not into the cycle, so there are 3 resources and 2 are into cycle and one is just allocated to some other thread, then we can say there may not be any deadlock. So there is a possibility, but it is not sure. We cannot say that by conformity that it would lead to a deadlock condition. So that we have to assess. So this is there are a few things that we checked for. The most important is to look for the safe state. If the state of what is safe state and what is state in the current snapshot of the threads, their resource requirement, their resource allocation, and what they are going to ask for next would create a state, and we have to look for whether the state is safe or not. We discussed about Banker algorithm. The Banker algorithm requires these 4 data: structure, available, max, all allocation, and need. Available is how many resources are available with how many k instances, let us suppose. Then max is what is the maximum need. So whenever a process enters into the queue, so it has to basically allocate, declare that how many maximum resources it will require for a particular, how many instances of a resource it will require for a particular resource. Then allocation is how many are allocated, and need we calculate. So whenever a question would come to you, 3 things would be given: available, like what is the max available for the system; maximum, those are needed for it; and allocated, already allocated resources to that particular thread. So based on that, we have to judge whether there is a safe or unsafe state, and the next request can be allocated to or not. So we discussed about the safety algorithm, and then we have resource request algorithm. We did one example, and I want you to do one example for me today. I'm going to write down the values. So allocation, let us suppose I have A is equals to 12, B is equals to 13. Can you take out your pen and paper and can you do it for me? And D is equals to, I think it's 12 again. So we will see. So now P1, P2, P3, P4, and P5 are your processes. Now allocations are what is allocated to them. This is 2 3 1 2 3 2 1 2 5 2 0 0 0 1 2 2 and then 1 3 0 2. If you are able to do it with me, that would be excellent. The max need for this is 3 3 2 4 4 5 2 3 6 3 1 1 1 2 3 4 and 4 4 1 2. Okay, now available are 1 2 3 4, and let's make need is equals to need is 1012. This requires 1012. This requires this minus this. It will be 1 3 1 1 1 1 1 1. And it requires 1 1 1 2. Then it requires 3 1 1 0. Okay, so now the question for you is find out the safe sequence. What is a safe sequence? The available resources now has decreased. Now the new available sources are, after adding these two values, after adding P2 and adding this. Okay, now the new available resources are 0 0 1 4, and with that let me draw all that. Okay, so P1 requirement are 2 3 1 2. New requirement after this is 2 3. This one 0 0 0 1 2 2, and then the new request would be adding after this. After adding this is 3 2 3 1 2, and the max would remain same. And if we calculate based on this, we will left with the available sources with this, whereas the need for this is 101 2 110 1111 1112, and then we have 11200. So if we can see on available resources, and we cannot allocate this to any of the processes, because based on this, we cannot even allocate this to P1, not to P2, not P3, 4, P4, and everyone would be stalled on this particular location where we have insufficient resources, and that's why all would be waiting, and this is not a safe sequence. Okay, so this sequence, after adding this, it is going to lead our system into unsafe state. So what would be done? This allocation would not be executed. It would not be executed. So the request for P5 for 1011 would be denied. If we deny this, we go back to the previous state, just allocating this, and then we would have a system which is in the safe sequence. So in that, where do you get the term? So I get terms from adding this. These are the allocated. Now the maximum I have are these are the max values of the resources which are available. Out of these, some are available allocated already, and available is equals to max available minus this, the allocated. So that would be giving you availability here. That's the remaining number of sources. Yeah. Okay. Thank you. So what is the step? The step is, let us suppose at time t0, you check for safe sequence. So how it is checked? You keep on adding the threads. The threads would have max requirement. Their threads would have requirements. Threads would have requirement means the max need of instances of all or different type of different resources, and we keep on adding the threads into the system. Let us suppose at time 1, we check for whenever we are adding and making the thread is making a request, we are allocating that request, and based on that request, it would be we would run the safety algorithm. If this request from a new thread creates a safe sequence or safe environment or safe state for our computer system, then it will be allocated, otherwise it will not be allocated. Okay, so I think it will check for safety. If safe, resource allocated. If not safe, request denied. Safety algorithm is very important to whenever a resource is requesting, whenever a thread is requesting for a resource, the safety algorithm will run. It will check for the safe state of the system. If it is safe, then resources are allocated. If not, then the request is denied. So based on this, the banker's algorithm allocate the resources, and this will create a safe sequence. Let us suppose P1, P2, P5, P4, and P3 is a safe sequence. So this is how the resource allocation would be done, and this would be executed in this way. So the need of P3 is satisfied with this sequence when all P1, P2, P5, and P4 are already executed. So this is how your safe sequence would execute. And if they execute in this way, there would not be an unsafe condition. If there is no unsafe condition, there is unsafe condition, then the deadlock can happen. If there is not an unsafe condition, then no deadlock would be happening. So if it is safe, okay, now next is deadlock detection. We discussed about deadlock prevention, then we discussed about avoidance. Now the third is detection. If we are not using deadlock prevention or deadlock avoidance algorithm, then deadlock situation may occur. And if it occurs because there is a cost involved with deadlock prevention and avoidance, we allow our system to go into deadlock, okay, because this is a rare condition. So we say, okay, if the deadlock would come, we will see it afterward, and that is called deadlock detection. Why we do that? Why we let our system to go into deadlock condition? Because number one, it would be rare if we have number of resources available. Number two, the cost of running deadlock prevention and deadlock avoidance algorithm is too high because we have to run it for every request. So rather than doing that, we try to identify if there is a deadlock. So we allow the system to enter into deadlock state. This is third way of handling deadlocks. Okay. Then an algorithm would run to recover the system from deadlock. So we allow the child to go into the jungle and we try to protect it if there is any problem. So that's something which we are doing here. And then the recovery scheme. So how to recover from the deadlock condition, that is also part of deadlock detection. Now, again, there are two types. If we have single instance of each resource, or if we have multiple instances of the resource type. So what would be there? So for that, there is a variant of resource allocation graph to maintain a weight graph. So there is a new graph that is developed here. Rather than resource allocation graph, we are developing here weight graph. Now the nodes are the processes here. So node, you'll see something like this. The nodes are circular symbols. So these are the processes. Then an edge from Ti to Tj is in a wait for graph implies that thread Ti is waiting for thread Tj to release the resource that Ti needs. So what we did is we removed the resources and then we added a wait edges. So if there is an edge from one thread to another thread, it means that thread Ti is waiting for the resource to be released by Tj. And an edge Ti to Tj exists in the graph if and only if the corresponding resource allocation graph contains two edges. It is what it is equivalent of resource allocation. There were two edges. One was the request edge, another was the assignment edge. So this was request edge. So Ti was requesting for RQ, whereas RQ was already assigned to Tj. So this is basically, these two are synonym or same. To detect the deadlock, the system needs to maintain the weight graph and periodically invoke the algorithm to search for cycle. If there is a cycle, so we set the period, like, okay, if you remember, there are few things which are done periodically. There are processes which for which there is no parent process. So in that case, system also run some parent processes periodically. So few things are already done, like to maintain the integrity of the system. So something similar is done, that the algorithms are run periodically, and this would search for the cycle in the graph. And if there is a cycle, it means deadlock has happened. So it will try to remove that and remedy. It will find out some remedy of that particular, instance or incident. So an algorithm detects the cycle in the graph requires O(n) square operation, which is too high. So, but still, these are graph problems. So normally in graph problems, the operations are like, the complexity of algorithms are very high. So it is O(n) square here. Now this is a resource allocation graph, and this is corresponding weight graph. So what has been done is, T4 is having a request edge. So this is request edge, and this is assignment edge. This has been removed by basically edge with the weight edge. So T4 is waiting for T1. So the resources are removed, only edges are left. So T4 is waiting for T1 to release the resource. T1 is waiting for T2 to release the resource. T2 is waiting for T5. Then T2 is waiting for T3, and T3 is waiting for T4. Do you think, is there any cycle here in this graph? Yes, so there is a cycle from T1, T2, T3, T4, and T1. This cycle is there. So obviously the deadlock has happened. So the algorithm needs to make assessments that we would be discussing shortly. And based on that, it will actually break this. It will try to break this cycle and try to free the resources. Now, if we have several instances of resource type, then how the deadlock detection algorithm works. So algorithm employs several time varying data structures similar to what you used in Banker algorithm. If you understood Banker's algorithm, then it is very easy for you to understand what is happening here. So it is also maintaining available vector of m length. Each indicates the available resource instance of each type of each resource. Then we have allocation, which is similar to what has been allocated to a particular thread for which resource and how many instances. Then we have a request matrix. So a request is something similar to need there. So how many are required? So this is the request that is the current need of a thread. So it will be showing that this particular thread needs k instances of each and every type. So if we say the matrix is there, so the total row A, B, C, D, this is for Ti. It will tell me that I need 5, 4, 3, 2. So it requires 5 instances of A type resource, 4 instances of B type resource, 3 instances of C type, and 2 instances of D type. So this is one vector. But if I say ij, so ij means this. It means that it requires ith thread requires these many instances of a type of the resource. So this is the meaning of this particular request matrix. So we have this whole n by m matrix, which is used and managed for requests. So similarly, this is what I was talking about Ti. Now this is the whole vector, which is representing the full request matrix or array for thread Ti. We go forward to work on detection algorithm. If you remember from the previous Banker's algorithm, there also we created two variables, work and finish. And work is the initial value of the work for any snapshot T0. is available. So why I'm writing T0 means at any instance when this detection algorithm would be running, whatever is available resource listing would be allocated to work, and then we run this algorithm, find and index I such that both finish I is equal to false. So if the allocation is not equal to 0, then the finish is false. Otherwise, finish is true. So we set up few values previously, the initial values, and then we run this. If finish I is equal to false and request is less than walk, then we say we go to step number 3, where work is new work. If you remember, we were updating available I is equals to available I minus 1 allocation. Remember this we did in the bankers algorithm. So same thing is here, because work is equal to available. So the new value of the work is equal to the previous value of work plus allocation. So, and it will set finish is equals to true, and we go back to the steps. So for each and every thread, we try to run this and try to make this finish is equal to true. This is something similar to what we did for the safety algorithm. The fourth step is a little different. There we were checking for if the finish I is true for everyone, then it means that the state is safe. But if here is if finish is equals to false for any value of finish which is equal to false, then we detected that the system is in a deadlock condition. So this actually checks for finish is equal to false, then array. If there is some value of that we got false for that, it means that there is an deadlock condition, and this algorithm requires m into n squared operation to detect whether the system is in deadlock state or not. So you can see that in the previous we discussed about n, and now it has become m into n squared. So certainly the complexity is more, but we would be running it less frequently, and with that we can save the resources for the CPU, and it will be better for us to manage it. Now the example is here. We can see that the snapshot is same. So there are allocations, there are maximum resources which are available, then certain allocations are already performed, then we have available. Do you think that is there any deadlock? Would you think that there would be a deadlock condition here? What would be done? T0 would be running because its request is 000. It's not requesting any other new resource. So it will execute. So T0 will execute. Then after this, the available resources would be available plus allocation. So now the new value of available would be 010. Here the request is 202. Available are 010. So this will not execute. T1 would not execute. Now we go to the next one. Here it is requesting for 000. It will run actually. This will run. And if this will run, new value for this would be 313. Now if this is 313, this requires 202. So it will execute and make this as 513, and then it will execute this, then it will execute this. So you can go by T0, T2, T3, T1, T4, or we go by T0, T2, then T1, then T3, T4. All are safe and the sequences are safe, so there is no deadlock condition that has happened. Yeah, so this would actually be letting us know that there's no deadlock condition has occurred. Now T2 request an additional instance of C type. So this is a new request. Can you check for whether this would create a deadlock condition or not? Do you think that this would lead to a deadlock condition? This says T2 has requested another resource 001. So now the new request from T2 is this. Okay, so we start doing this. T0 would run because it does not require any resource. So the new available would be 010. Now in this state, this requires 202, this requires 001, this requires 100, this requires 002. So with these resources, it cannot go. So when we have these resources, the system is in a deadlock state. So basically with this request, the system now is in a deadlock condition, and we can actually check for the deadlock has occurred, and which deadlock suffering. All resources which are suffering here are T1, T2, T3, and T4. T1, T2, T3, and T4 are basically those processes which are just stopping there and not making any progress. Now, how to use this detection algorithm, and what would be the recovery of it. This is what is pending. So the frequency, how often you want to likely that you expect the deadlock would occur. So there are some benchmark experiments they usually perform, and that is beyond the scope of this course. So to test like how often that would occur. So this is a judgment, this is a experiment that we run, because for each and every computer type, like whether you are running a desktop computer or your mobile application or it is a server, there would be different type of jobs those would be running, and based on those jobs, the resource requirement would be happening. So if we have a similar type of job, it means that the similar type of resources would be used, and in that case we need to either increase that same type of resources, or we need to detect the deadlock more frequently. So it depends upon the type of the system and operating system where we are using, how often we should actually run this deadlock detection algorithm. And if the deadlock has, we have detected the algorithm, now what would be the remedy for that? The remedy for that is, let us suppose the deadlock has occurred. One remedy is I terminate all the processes. So this was out of the deadlock. So I terminate all these processes. This is one way of doing. All processes are terminated, and the system becomes deadlock free. Now this creates a problem, because when a process runs, there is a cost associated with that process. It may be possible that your process is about to finish. There is a very costly process, as we discussed in the previous lectures too, that the cost is always, the batch processes are the lowest priority processes, and they run in the background. If somebody wants to make it high compute, then they have to pay extra. So same is happening on clouds also. So if you need more resources, you need to pay more, and based on that, these selections are made. If a process is very costly and is in a deadlock condition and we terminate it, certainly we have to restart the process, and it would be very costly as well as time consuming for us. So that is one approach of doing the recovery. So how many processes need to be rolled back? Either all or one. If we actually terminate, rather than all terminations, we terminate one, because that would break the cycle. There are two solutions to it to break the cycle. Either add more resources, delete one, or terminate one process which is in that particular cycle. So which one should be deleted? Let us suppose there are T2, T3, T4, T5 are in deadlock. So which one is to be selected? It may be your favorite number. Okay, so you can go 1, 2, 3, 1, 2, 3, 1, 2, 3, and then you go for that. But that's not the way the logical thing is. It is one thing, one with the lowest priority, and one which has just started, and we can always think of the priority and how it is, and the number of resources that it requires to execute. So there are many things that we combine together to make a heuristic about terminating one process. So this is heuristic algorithms that we implement, that which should be chosen as a victim. So whenever a deadlock is identified, the next step for the operating system is to choose the victim. So the same thing is happening in databases also. So whenever there is a deadlock detected, then a process is identified, which is called the victim. It is terminated, and it is rolled back to the previous state. If you have worked on databases, then you are aware about rollback and commit, two commands. So rollback is moving the process back to the previous consistent state. So if there is a deadlock, we terminate the process, the victim of the deadlock, and we roll back that to the previous state. So because we always want that the processes should not be terminated abruptly. They may have made some changes to the variable and the values. I suppose your process is basically removing some amount from one bank account and putting it into a different bank account, and within that scenario, it hangs into a deadlock. So it has deleted some amount from or fetched some amount from the one account, but it was now into the deadlock condition, and we terminated it. What would happen? The deletion to the other account would be significant, and this has not been added to the next account. So this creates an inconsistent state, because it has removed some value, some money from one account, but was not able to add that money to the next account, because these are instructions. So if we are taking out some money minus, then we are doing some plus. So within that, deadlock occurred, and we identify that as a victim, and we remove that, and that would create an inconsistent state for the values. So this is what should not happen whenever we terminate our process. So for that, whosoever is selected as a victim, we say that it should roll back to the initial state and it actually started. So the rollback is always applied for doing that, to make the data and its changes into a consistent state. So if deadlock has occurred, then it should be invoked frequently, and then we have recovery from the deadlock. So when we have detection algorithm running, it may be that there are several alternatives available. One possibility, when deadlock occurred, basically we deal with deadlock manually, or another possibility, we recover from deadlock automatically. These are two possible situations. So this we have already discussed about all deadlocks, or about one deadlock at one time. So finding out the minimum cost is dependent upon the priority of process, how long this has been computing, how many and what type of resources in the process has used, how many more resources this would need, and how many processes will need to be terminated. So these are few things, rules that we have to apply before we actually terminate the process. If we want to terminate the process, we have to select the victim. So obviously one with minimum cost. So the cost factor we have discussed here. So these are the cost factor that are used. This is not the exhaustive list. We can add more to it. So once we identify the minimum cost thread, we identify this as a victim, and then we roll back all the changes it has made. This would create, and this can create the starvation. Like if we this at same time the same things are happening over and over again, and the same victim is chosen again and again, then we need some mechanism by which we can identify that the same victim should not be selected every time. So for that the starvation should not happen, the most common solution is to include the number of rollbacks as a cost factor. So we can add the number of rollbacks to that particular process. If it has already happened, then we should not be selecting this as a victim. So this is how we actually select the victim and then perform our deadlock recovery. We have, let us suppose initially we have resources R1, R2, and then we have thread it is allocated to, and then there is another thread T3. It may grow. So it has requested R1, this is R2, so this is like this, and this is like this, and we just okay, I take just two. Now how we are increasing, because this is a cycle now, because this was free, so deadlock was not there. It could increase. Let us suppose another process has been added here, which was requesting for R3, and it is allocated to this, and now this was allocated to this, and this is requesting on this. So something like the new processes could be added as it is still waiting. So there may be other resources start waiting for it. I suppose there is T6 started waiting for requesting for this, and it also start requesting for other processes. So I mean to say this graph can increase more, because deadlock is what? Deadlock is that the resources are blocked. There would be new processes, those would be keep on adding as the system is running. So they would also stall on as they require the same resources. So this could actually increase. The number can increase, and there would be new additions, those can happen. So that's why it is written that the cycle and the size can increase over the time. So with this, we finished our chapter